We're starting section 4.5, L'Hopital rule and indeterminate forms. Little refresher. First we discussed the determinate and indeterminate forms, and then we discussed the L'Hopital rule, and then we discussed comparing the growth of the function. That's something that we see with the L'Hopital rule a lot. So the discussion of a form of a limit, when you plug in the value, if you have limit as x goes to c of something, you plug in that c in there, and not necessarily always a number, and sometimes you cannot say if it's an infinity or what is it. And so in here, let's see, the first example, limits of x to the power arctan of x as x goes to 0. If I plug in 0, I get 0. Arctan of 0, also 0, so 0 to the power 0. Here, as x goes to infinity, it's infinity to power 0. And that's the form. And then if I plug in 0 in here, I get 1 to power infinity. That's the form. As x goes to 0 from the right side, natural log of x goes to negative infinity, and sine of x goes to 0, so it's 0 times infinity. And a lot of times you see that people omit that negative or positive. But overall, what we say as indeterminate forms, and they are 0 over 0, positive or negative infinity over infinity. Again, it's just infinity over infinity in my mind. And then plus or minus 0 times infinity, 1 to infinity, 0 to 0, and infinity to 0, and infinity minus infinity. These are the 7 forms, and we would like you to actually memorize this and know what forms are indeterminate forms. And so when you get any of these, you have to do some simplification to figure out if the limit exists, and if it exists, what value it is. Now, let's discuss a few limits of 0 over 0. From the past, we know limits of sine of x over x as x goes to 0 is equal to 1. We also know this is a form 0 over 0. Another form 0 over 0, if I plug in, I get 0 over 0 is sine squared x over x. You can basically simplify this and see. And so one way of finding this from the information that we have from before is to setting it separate as this. And this part goes to 1 and this part goes to 0. And so this, with the same method of separation, we see that actually one of the limit does not exist. So this one, the limit of sine of x over x squared, if I do the separation, this time is sine of x over x times 1 over x, and the limit doesn't exist. If you limits of infinity over infinity, this one we know from pre-calculus. Polynomial of the same degree in the numerator and the denominator, as x goes to infinity, it gives me the coefficient between the ratio of the coefficient, which here is 1 over 1. Now, there are a few things that we don't know, basically. I don't know what the limit of a natural log of x over x is. It turns out it's going to be 0. And I don't know what's the limit of e to the power x over x is. It turns out that it's infinity. But the way to know this, these are both infinity over infinity, and the way to figure these two out is only with L'Hopital rules. And so basically there are questions that we posed over here that are going to be also solved with L'Hopital rule, and sometimes some questions are less computative if you solve them with L'Hopital rule, but they have other methods to solve them. Some questions are more computative if you solve it with L'Hopital rule, but they can be solved with other methods easier. And then some questions only can be solved with L'Hopital rule. Some questions cannot be solved with L'Hopital rule. So something else to notice is that between the 0 over 0, infinity over infinity, it's always you don't know whether or not the numerator is more strong or the denominator is more strong. We call it tugs of war between them, and so we don't know which one's growing faster or which one's growing slower. And so when you solve the limits, then you know which one's growing faster or growing slower, or you find the value of the limit, and so this is also, and sometimes, for example, for these two, we need the L'Hopital rule to figure out which one grows faster, which one grows slower. So L'Hopital rule is this: if f and g are differentiable near x equal to a, and either limits of f of x is equal to 0 as x approaches a, or limits of g of x is equal to 0 as x approaches a, or limits of f of x is equal to plus minus infinity as x approaches a, and limits of g of x is equal to plus and minus infinity as x approaches a, then the limit of the quotient in either case is going to be equal to limit of the quotient of the derivatives, that is limit of x as approaches a of f of x over g of x, it's going to be equal to limit of x approaches a of f prime of x over g prime of x, if this limit, the second limit, exists. So this one has to exist, and then the limits these rules also apply for one-sided limits. So there should be differentiable, and then you can replace the, again, if and they are 0 over 0 or infinity over infinity, then you can use the derivative of the numerator and the denominator. That's about it. Again, derivative of the numerator, derivative of the denominator makes a new limit, and that limit is going to be equal to the original limit, and there is a condition: f and g have to be differentiable, and it has to be 0 over 0 or infinity over infinity, of the form 0 over 0 or infinity over infinity. Okay. So let's do a few examples. Example 1 part A, and let's see, these are the ones that are 0 over 0, form 0 over 0. And so what we do is we mark the step that is called L'Hopital rule step by LHR. And so now let's go. Limit of sine of x over x. I know it's 0 over 0. I know the limit also, but let's try it using the LHR. And that would be, I have to replace this here. This one gets replaced by its derivative. That one gets replaced by its derivative. And so I get on top, I get cosine of x. On the bottom, I get 1. And limit still as x approaches 0. And then limit as x approaches 0 of cosine of x is going to be 1. Which step was LHR? This was the LHR. Because I took the derivative of numerator and replaced, and derivative of the, again, another thing too, it's important to know is that this is not the quotient rule. This is just the L'Hopital rule. L'Hopital rule is for limits. Quotient rule is for taking derivatives. L'Hopital rule uses derivatives to find limits. The second one of these is the limit as x approaches 0 of natural log of x squared plus 1 over x. Natural log of x squared plus 1, if I plug in 0, I get ln of 1, which is 0, and then over 0. So the form is 0 over 0. Now, can I use the LHR? So let's try to use the LHR. Again, take the derivative of the numerator, put it over here, derivative of denominator, put it over here. Don't forget to put in your limit, because this is not equal unless there is a limit between them. The limit is there. And so now here, derivative of natural log of x squared plus 1, derivative of the numerator inside, which is 2x plus 1, divided by the inside. Derivative of x is going to be 1. And now I have this limit. Two ways of doing this. I know already how to find that limit sorry, there was a little error. The limit is the derivative of inside is 2x. So it's 2x over x squared plus 1. And here, if I plug in 0, I get 0 over 1. And therefore, it's not an indeterminate form. And it's going to be 0. 0 over 1 is 0. And so I'm done. So we saw a bunch of examples. We saw an example that actually we knew what the value was. We saw another example that we didn't know how to do from other methods. And here's another example that, let's see, if I plug in x equal to 2 on the top, I get 16 plus 4 plus minus 20 equal to 0. And the bottom, I get 8 minus 8, which is 0. So it's a form 0 over 0. And I know that when I have polynomials of the form 0 over 0, I have to factor and simplify the 0. The factor that contains that 0 from top and bottom. Here, notice that the factoring of the top is kind of difficult, and I would, most times I would do long division to factor that. I know that x minus 2 is a 0, then I would do a long division to find what multiplies x minus 2. And the denominator is easier to factor, but because of the rule, but still. And so this seems to be much easier using L'Hopital rule. And so let's use L'Hopital rule. Again, limit as x approaches 2 is the same. Then you have to take the derivative of the numerator, put it in here, which is going to be 4x to the third plus 2, and the derivative of denominator, which 3x to the 2. And now, if I plug in 2 in here, I get 4 times 8 plus 2, which is 34. And then if in the bottom, I get 12. So now I can plug in and I get 34 over 12. And so that's much easier than factoring. And now some limits of the form infinity over infinity. And then again, we use LHR to show that L'Hopital rule was used. Over here, limit of 3x minus 7 over 6x plus 5. If I plug in infinity, it would be form infinity over infinity. Now, that's not going to work that way. So let's find, one way is to solve the way we know from the material before, and the other way is just using L'Hopital rule. So first you put the x going to infinity, and the limit, then you take the derivative of that part, it goes here, derivative of that is 3, derivative of this is 6, so the answer is 1/2, which is what you expect because the coefficient of the higher coefficient of the leading coefficient on the top is 3, the leading coefficient on the bottom is 6, and limit goes as x goes to infinity, and the degrees of top and bottom are the same, numerator and denominator. Therefore, you get the ratio of the two coefficient is going to be the limit. Now, how about limit of natural log of x over x? And this one, I don't have any other method, so let's just use L'Hopital rule directly. So again, limit as x goes to infinity. Wait, the one thing that I didn't write down is form is infinity over infinity, natural log of. If I plug in infinity, natural log, infinity, and the bottom is infinity. And so now, so the derivative of natural log on top, derivative of the x on the bottom, what I get is a natural log. The derivative is 1 over x, the bottom is 1. And so limit of 1 over x is goes to infinity, and that is 0. Okay, so the limit is equal to 0, and notice this means that between natural log and x, natural log is a stronger, and natural log is a weaker infinity, and x is the stronger infinity. So at infinities, natural log is not growing as fast as x. So next question. And here's the next question. Natural log of x over natural log of sine of x. Which one wins? And so as x goes to 0 from the right side. Now, again, I'll plug in 0 in here, positive 0. I get negative infinity, and same thing in the bottom, negative infinity. So the form negative infinity over negative infinity, it's infinity over infinity. Now, can I use L'Hopital? Yes. And let's see, limit as x approaches 0. From the right side, natural log of x, derivative of natural log of x, derivative of natural log of sine of x. This is equal to limit x goes to 0 from the right. The derivative of natural log of x is 1 over x. Derivative of natural log of sine of x is 1 over sine of x times cosine of x, which is the derivative of inside. Now, at this point, if I plug in 0, I get infinity on top, and I get infinity on the bottom. And if I want to do another L'Hopital rule, it's going to be a little awkward, and derivative is a little harder. So what I do instead, I simplify this, and I get limit x goes to 0 positive, and 1 over x times the reciprocal of the bottom, which is sine of x over cosine of x. So it would be sine of x over x cosine of x. Okay, so at this point, I know something for sure. I can separate this sine of x over x and limit of 1 over cosine of x. X goes to 0. First one is 1, the second one is 1. We end up with 1. So this limit also, this limit is 1. So natural log of x and natural log of sine of x, they have the same growth rate at infinity. Now let's go to iClicker question 1. Let's evaluate this limit. So I suggest taking a pause and coming back. So again, if I plug in 1 in the top, it's 1 to the power 3 minus 2 minus 5 plus 6 is a 0. If I plug in 1 in the bottom, I get 1 plus 4 minus 5, 0. So a form is 0 over 0. Now, can I use L'Hopital rule? Yes. Should I use other methods? No, because factoring is going to be a kind of a hassle, and you have to do long division for this one also. And limit as x goes to 1, and I get 3x squared minus 4x minus 5, and then I get 2x plus 4. Now if I plug in, does that give me a number? Yes, it gives me 3 minus 4 minus 5, that is minus 6 on top, and on the bottom it gives me 6, so the answer is -1, and B is the answer. Now let's go to iClicker question 2. Evaluate the limit of sine squared of x over 1 plus cosine of x as x approaches pi. So this one, let's take a pause and then come back to it. After the pause, I realize that if I plug in pi on top, I get 0. If I plug in pi on top, I get on the bottom, I get 1 minus cosine of pi, which is -1, 0. So form again is 0 over 0. Therefore, I can use LHR. And then limit as x approaches pi, limit of sine squared of x is going to be 2 sine of x cosine of x by chain rule, and the limit of the denominator is minus sine of x. Now at this point I know that I can simplify the sine of x from top and bottom, and I end up with limit as x approaches pi of negative cosine of x, -2 cosine of x, and that is -2. Oh, cosine of pi, when you put -2 cosine of pi, which is 2. And the answer is 2. D.